So we are given a tree with n vertices, and we have to do cleaning operations on the tree. In each operation, we have to choose two different leaves, and this would clean all the edges on the path connecting the two leaves. The cost of the operation is the number of edges on the shortest path. Also, there's a condition that we can choose at each leaf at most once in across all operations. The total cost of the cleaning is sum of the cost of all the cleanings, and we have to minimize the cost. So suppose we are given a tree. Let's say we are given this tree, and now we choose these two vertices. These are leaves. So in the cleaning operations, these four edges will get cleaned and the cost will be 4. Now, suppose we choose these two, the cost will again be 4 only clearly. And now suppose we choose these two. These are connected by a path of length 2. So the cost will be 2. Now if you notice that this path covers these edges, these cover these two, and all the edges are covered and the total cost is 10. Did you all understand the problem statement? Yes. So if the number of leaves is odd, then it's clearly impossible to clean. Since one of the leaves would never appear in operation, each leaf can appear at most once. And if we do X operation, 2X leaves appear. So one doesn't appear and the edge connecting that leaf and its parent is never considered covered by any other operations. So if the number of leaves is odd, it is impossible. And now we have to check if the number of leaves is even. So first I'm solving this problem, like how to find if a tree is cleanable or not and how to find the minimum cost. And then I will show how the updates are handled using HLD. So now suppose this is an edge and there are two subtrees hanging on both sides. Now if you notice that there are an odd number of leaves here and odd here, then there is at least one operation which passes through this edge, right? This is always needed since each edge need to be cleaned. At least one operation is needed, and either ways, if every leaf is in operation, or like even of this side are together, and so one, at least one must cross this edge. And now in the other case, when the subtree sizes are even, since the edge needs to be cleaned at least once, there is a node in this which connects to a node in this, pairs with a node in the other side, and now an odd are left on each side to yet to be covered. So there is one more, or one which passes through this. So there are two pairs of nodes such that this edge is cleaned at least twice. So if in even subtree size the edge is clean at least twice and in odd it is clean at least once. So did everyone get this part? Okay, so now it turns out that these are sufficient conditions also. So let there be X edges with even subtree size on both side. Even not subtree size. By subtree size I mean the number of leaves only. With even Y edges with odd. So answer is greater than equal to 2x plus y always, right? Since I showed that two edges pass, at least two edges pass. Yes, y is equal to n minus 1 minus x. So if we just find the number of, okay, so now the main claim is answer, we can actually find a construction which attains this exact value, which we showed that the answer is at least this, and if we find a construction which attains this exact value, we are done. And so now if I will show this later, but suppose 2x plus y. So now we only need to find the number of nodes with even subtree size, and then we would be done. Since x plus y equal to n minus 1. And now proving that statement is not very difficult, I will give small hint, and I will like we will use induction. So suppose we are doing DFS, and if a node has odd subtree size, we will make sure that only one node is left out, which needs to be matched with some node outside the subtree, and the other even nodes are matched between themselves only, and all the edges in the subtree are covered. Obviously the path from that one node must cross this vertex and its parent, the edge to its parent. And for even subtree sizes, this is actually odd, so I will add one more. For even subtree sizes, there are two such nodes, at least two such nodes will pass over this edge. Now it turns out that we can maintain a sort of an inductive argument. So suppose a node is there, and like for each edge we have either one or two nodes covering it, and we somehow need to match these nodes together and have one or two nodes leading outside. Okay, also the number should be 0 if it's the root node, but if the subtree size of this is odd, then one node should be left out and rest will be matched. If it's even, then two should be go out and all rest should be matched. So if you now notice that this can always be done, like the exact rigorous proof is left as an exercise to the reader. So did you all get this part? Yes. So if the subtree size is at least 3, then you can connect to arbitrary nodes within it. Not exactly arbitrary, but like if we have processed the subtrees, the children of the nodes, then we only need to care about the edges outside of the children. So only these edges, which will be covered by at least one or two nodes leading outside of it, and all the edges outside. So now if we can, let's like suppose we need two nodes to lead outside. We can match one from here to one from here, one from here to one from here. Now one is left here and one is left here, and these two go up and connect to some other leaf later. So did you all get this part? So now problem reduces to finding 2x plus y. X plus y is n minus 1. So we need to find n minus 1 plus y. Basically, we just need to query the number of nodes with even subtree size. So like if there are no updates, we can just like trivially see the number of nodes with even subtree size. Yes, you are right. N minus 1 plus x. Now there are q variations of the tree in the problem. In the ith variation, the person adds di extra leaves to the original tree, and then those extra leaves are removed, then some other variation is done. So now there's a constraint that sum of di is at most 10 to the power 5, and the new leaf node is added to a original node, which means it must be between 1 and n. So it won't happen that we add a node to a current node and then we add another leaf to a newly added leaf. So suppose this is an original tree. Now there can be, suppose there are three new leaves added, one to this, one to this, and one to this. And now we need to find the cost of cleaning the tree for this tree. So basically we only need to maintain the number of vertices with even subtree size. And now I will show how we can do this using HLD. So in a segment tree, for a node, we will label the nodes by their, by the way we will label by their start times in the DFS order. For a node AI, We will label it as 1 if even, subtree size, and 0 if odd. So we only need to like query the sum of all the nodes, and then we would solve the problem. We won't query for the root node since there is no edge leading outside of it, so that is a bit irrelevant. And obviously we need to check the trivial condition that there are an even number of leaves. If there are an odd number of leaves, we can directly exit. And now if you notice that if a leaf is added, the parity of the subtree size for all its ancestor changes. So if it was odd, it changes to even changes to odd. And also notice that the newly added leaves are also there. So all the newly added leaves, if you notice, they have subtree size of 1. So we need to add for x, we will add that also, and we will adjust n also according to the new size of the tree. So for now we only need to, for the original vertices, we need to find the number of nodes which have even subtree sizes. And now if you notice that if a node u is added to a node I, then for all the nodes from I to the root, the parity changes by so it just flips. Now if you notice, we are maintaining 1 if even size and 0 if odd, so we can just flip the vertices. So this is a XOR operation. And now in a segment tree, we can maintain, for a segment L to R, we maintain number of zeros, and number of ones is just R minus L plus 1 minus number of zeros. And so now we can find the number of zeros and number of ones easily if we see the root node. Now if you notice that a update from a node to its parent is a path, using a previous heavy light decomposition algorithm which I explained in the previous session, we can break the path into log n paths. We can do the XOR operations on the segment tree on all the log n ranges, and then we are done. We just need to query the number of 0 and number of ones is like n minus number of 0, n minus 1 minus number of zeros. So did everyone understand? Yes, an added node will always be a leaf node, that's given in the problem. So did everyone understand the solution? And then I can explain, go over the code. Okay, so this is the only like standard stuff. We calculate the depth of a node, the parent, the start times, the DFS too. We also like we maintain the start times. This is subtree sizes actually, and in this we find the label to the previous node. This is just the same, similar to code to what I showed in the previous problem. So I will now go over the main part. We maintain a segment tree. And the update operations, we for a range we just XOR all the values. So for a node, the value just changes to R minus L plus 1, the size of the range minus the previous value. And this is a lazy propagation, so we just do it for the children also. Like this is all standard stuff. This is the heavy light decomposition part. So for a node from I to its ancestor J, we just keep going to up the heavy and light edges. So suppose for a node, we go to its, these are heavy edges. These form a consecutive range, so we can do a range operation on them. and then there's a light edge, so we do the operation separately for this. Now there's again heavy edges, and we do the operation for them. So since there are at most log n right ranges, we can do order log n operations on the segment tree. And so it's each operation is like log n, we can do in log square. We can solve the problem in q log square, not q but like sum of di. So in each query, as you can see, we are given some set of newly added leaves, and we just need to do the update operations for them. And after this, we just do what I told earlier, x plus n minus 1. And also, if the number of leaves is odd, we output minus 1. So did everyone get it? I will also send my code for future reference. Yes. Since it's part 2 root, we will have login instead of 2 login. Actually, it does not matter much since it's order login. So yeah. So I like this problem a lot, especially not just the heavy light decomposition part, but the odd even part, subtree size part is very clean and it's very neat. And like I think as an exercise, you all should try proving it the rigorously that the you can find a construction of size 2x plus y. So you can try proving that rigorously. Thank you.